Great, good morning. So how's the projects coming along? It's due on Friday, right? Are you guys done with the projects? Some of you mentioned that your multi-threaded application is actually slower than the single-threaded application, right? You actually find that even with 4 threads, it still takes more time than a single-threaded application, right? How many of you noticed that? So one way you can do that is to kind of like scale the problem, right? Usually when you scale the problem, it might show up. You don't have to do that for this project, right? But instead of 512 by 512 array, if you do 1024 by 1024 or something big like that, hopefully the threads will have enough work, right? There's overhead in creating threads, and that's what you're probably facing. There's overhead in creating threads, and at some point you hope that the overhead would be offset by having multiple processes, right? But you may or may not. But so you can look at the profile and stuff, and that brings us to the reason of why we spend so much time on the processors and these. You spend 2 modules for processors and threads and how to make them work and everything, right? And we'll have 1 module for storage and 1 module for memory. This is precisely because this is kind of tricky business, right? I think I sent mail to most of you who got below the median, email saying if there's anything we can do. If you think about it, half the class has to be below the median anyway, right? Even if I wanted, it's not possible for all of you to be above the median. So just because you're below the median does not mean that you're doing poor, but I would like to see what we can do at this point, because like I mentioned, we still have 78% of the grades to go, rather than if you come in like week before the final grades are due, there's not a whole lot we can do, right? I'm not precisely sure what we can do. I suggest that you read the chapters before you come to class, and suggest you ask either questions during the lectures, or afterwards you can send emails so I can go over some of the materials again. One thing to remember is we have to sort of cover the first 4 modules. The last one is dispensable, right? Last one goes through topics which I can see getting rid of, if that means that we can spend more time on the first, at least a few modules, right? As a core course, you have to know all this stuff. The last module touches on topics which are important, but you can always get that from a higher level class. You're not going to go through another class which will talk about deadlocks and all those stuff, right? So if anything is not clear, let me know. So for example, we can go over the stuff again on Friday rather than going to the next module, right? So the way I had it planned, we keep going from one module to the next module and so on and so forth. But feel free to send me an email. I'll probably put up a survey on SurveyMonkey or something so I can say it anonymously. But I don't mind if you send it to me non-anonymously either, right? So if you don't say anything, I assume that everybody's catching up to where we are. And after this module, we're kind of done with the processors and we move on to the next one, right? I hope the project is helping you realize how tricky the whole notion of threads are, right? The funny part is, when I talked about first module, I basically said there are a lot of tricks that you can use up your sleeve to make these problems go away, right? You can cache it, you can do certain things like this to make the problems go away, right? And if you look at the first module stuff, the 3rd and 4th module, if your system does not have enough memory, right, adding more memory would most likely solve the problem for the most part, right? If you don't have enough storage, adding more storage would solve the problem. If you don't have enough CPU, making the CPU faster would solve the problem, right? So if those are the 3 parameters, we were in good shape. Unfortunately, because of the hardware, you can't just make the processor faster, right? If you find that the OS is getting slow, you can't just crank up the speed, because the hardware folks tell us that they can't make the processor any more faster, right? So for physical laws, you have to go to multi-core. So the little tricks I said do not really work here, because you can't just crank up the speed. So when you have 2 threads, each are doing independent stuff, right? You have to kind of harness them. You don't want them to go in lockstep, but you want to let them go as free as possible, but still be able to kind of have a predictable answer, right? If some of you are willing to walk over to the front, I can demonstrate what the thread paradigm does and why it may be confusing, right? Can I have 2 volunteers who would come here and do mindless stuff because your processes, you don't have to really think about it. That'll be good. Okay. So we are going to implement an algorithm, right? So let's think of the homework project, right? This is matrix 1 and this is matrix 2. You're going to go through the different rows, right? And you're going to go through different columns, right? And let's assume that V3 are threads, right? And if they're not threads, we cannot say, I go through that row and this column, modify this, that row, this column, modify this, and so on and so forth, right? Let's have more columns here, right? And the whole thing that you're trying to do is you're trying to let us go fast as possible, right? So I'm going to say our delay would look at 1, 2, and 3 columns. So let's say this is 1, 2, 3, 4, 5. There's 6 columns, right? And we kind of split, or maybe let's say 7, right? We kind of split the work where she'll look at 1, 2, and 3. Joshua will look at 3, 4, and 5. And I look at 6, 7, and 8, right? You had some bug, right? You wanted each of you to look at different rows, but because of some bug, we had 1, 2, and 3 assigned to her, and 3, 4, 5 assigned to him, and 6, 7, 8 assigned to me, right? So the way we're going to work is you have to keep doing 1, 2, and 3, meaning you go over there, think for a little bit, where you're trying to calculate, let's say 1, right? Which means that you have to look at row 1 and column 1, and you're going to update it, right? So you're going to think for a little bit, come over here, modify this, go over there, think for a little bit, and modify this, go over there, think for a little bit, modify this, and then you're going to do the same thing, right? You're going to go over, think for a little bit, modify this, modify this, modify this, and I'm going to do this, right? And hopefully we are doing it thinking at different speeds, right? So when you're thinking about a threaded program, this is what happens, right? We kind of assign the jobs to different people, and then we say go, okay? Do you understand what we're supposed to do? So you have to go here, think for a little bit, and then you have to go back here and modify whatever, right? Let's say there's no, right? Sorry. This is essentially what is happening, right? The threads are going at different speeds, right? So can you see a pattern? Like you are sitting there, can you see a pattern of what's going on by looking at what we're doing? Do you see some sort of a nice pattern as what would have happened if we all did in lockstep, right? So let's say look at it in lockstep, right? Lockstep is we'll all go and do the same thing at the same time, right? So in lockstep, you would say, now let's go, right? We go and you modify, she modifies 1, and you modify, what do you have to modify? I modify, then we all go, right? So it's kind of easier for you to see what's going on, right? Single threaded kind of thing, where we all go at the same, you all have to kind of keep up, right? So you all go modify, we all kind of go modify, right? But in the first case, if you look at it, it looks chaotic, right? Because I was going at different speed, she was going at different speed, he was going at different speed. And when you have a bug, right, when you are both modifying 3, which you shouldn't be, you as a programmer looking at it, you have to kind of see, I mean, they're going as a thread, right? So you have to kind of see this happening in time, right? So I think yeah, we are done. Thanks for monitoring, right? So was that helpful? So really, you are having all these things going through. So when you look at this, it should look chaotic, right? So I was kind of going in here, she was going in there, and Joshua was going in there. There is no one specific order, even though each of us were following a different order, right? You as a programmer would have to make sure that we spend enough time thinking and not enough time modifying the stuff. When you have problems in the code, it's kind of hard to figure out. If for some reason, if they're both locked or deadlocked, right? My job is to keep doing what I have to do. So I keep going, right? I don't actually stop for them. I don't look at what they're doing. So deadlocks are very hard to see because there are some parts of the program which are still making progress. And you don't want to slow these things down so much that everybody goes in lockstep, everybody does the slow kind of stuff. You want people to go as fast as possible, but debugging is harder. Understanding what's going on is harder. So I want everybody to go off at whatever speed, but still get something, right? And that's the challenge here, right? The more processes you have, the more of us you want to do something independent, right? And it may so happen that I may be faster than somebody, or she may be faster. You know, there may be older thread, newer thread, whatever. But essentially, you want to. So if you were to debug a thread program, you see this chaos. You have these 3 threads doing different stuff at the same time. You have to kind of guess where they're going and make sure that they're kind of following some rules. And some of the rules are what we are looking at in this. The atomic transaction, all those things are kind of some rules to say, you go as fast as possible, but we still have some rules, right? So it may be tricky because most of you are probably used to thinking about programming as this single flow of control, right? You program, you do one thing. There's only one thread doing different stuff. So you know precisely what has to happen, right? Now we have to assume that, okay, while this thread is doing something, this thread may be doing something else, this is maybe doing something. So practically you have to think in your brain, you have to have many threads in your brain, right? You have to kind of say, this is how my algorithm would have to work and go with that, right? And if you really do a good job, you could get 3 times the speed up. The more you have to make, the more your algorithm has bugs, the more you have to fall into some of these things. You don't get the speed up, right? So this model was not expected to be easy or trivial. In some sense, it touches on programming more than the operating system, right? As we'll see, the operating system can just give up and say, it's all the programmer's fault. Most operating systems that you see commercially does not do many of the stuff we talked about, the deadlock and all those things, right? And one reason might be because we didn't have multiple processors before, right? It used to be on the servers, but on the normal desktops or laptops, you didn't have multiple processors. So operating systems can say, we don't deal with deadlocks, we don't deal with any of those stuff, you're on your own. But it may not go on like that forever. You may, as we have more and more processors, as the hardware folks tell you that there's going to be more processors, you would have to deal with those stuff, right? So if you're going to be a programmer, if you can't use the different processors to harness them, then you're not going to be a good programmer. If you're not going to be a programmer, if you're going to be a manager or so, you still have to understand what are the challenges, right? And you cannot say, well, let's get more processors and we'll solve the problem. It's not as trivial as that, right? But if any of this stuff is, it's not clear to you, let me know and we can go over them, right? So if it helps to go through a program to explain all the stuff we talked about, we can do that or what have you, right? Make sense? So there are no handouts today because we are still following from the last lecture's slides. So we left off with looking at the banker's algorithm, right? Which is there to figure out if there's a deadlock. So we define notion of a safe state, unsafe state, and a deadlock state, right? And banker's algorithm really tries to figure out if some safe state is safe, right? Meaning, if you do this allocation, there is no possible way that you can get into deadlock, right? And as we saw, there's a safe state, an unsafe state. Unsafe state means that you could potentially get into a deadlock, but doesn't mean that you have to be in a deadlock, right? So for this algorithm, each process has to say how many resources it wants upfront, and the operating system has to keep track of how many resources have been allocated. So based on how much you wanted and how much has been allocated, it knows how much you can potentially need in the future. So what we call as need is basically what you might need in the future. What you call as max is what you wanted from the system. And what you call as allocation is what was given to you, right? Just because you have a max does not mean that, just because you have max and need does not mean that you will have to get those, right? You ask in the future. So what you're trying to see is, at this instant, if you come in and ask for more resources, if one of the processes come in and ask for more resources, if I give this to you, in the worst case, will I go into deadlock? In the worst case, is it safe, right? It's not the best case. In the best case, I may give you the resource, and somebody else up here may finish immediately and never ask for the need that they asked for, right? So you're not looking for the best case, you're looking for the worst case. In the worst case, if all of the rest of them come back and ask for what they want, can I do that, right? And the bankers algorithm works in the same model, because if you give credit limit to different people, you're trying to see, in the worst case, if all the customers come in and ask for their money, can I give it to them, right? I'm not giving it them immediately, but I have to be able to give it to them through some way. I'm hoping that somebody would pay back their loans and I can eventually give it to them. But so that's a banker's algorithm. In real life, banks don't work like that because they have enough money that they kind of borrow around from different places and they default and all those things, right? So we're not worried about those, right? So here's the example of one such instant, right? So in this instant, there are three resources, A, B, and C. So before we proceed, what do you think these resources are, right? We talked about different resources being, some of them being preemptible, some of them being non-preemptible, right? Remember when we talked about the conditions for deadlock, right? So what kind of resources do these A, B, C have to be? If you were to implement this within an operating system, what kind of resources would A, B, and C have to be? Are they all resources, only preemptible resources, only non-preemptible resources? Yes?
Would that be preemptible?
Yeah, it will only have to be preemptible, right? Because remember, the condition says for deadlock to happen, all the conditions have to be true, right? It has to be, so it has non-preemptible, right? Did you say preemptible or non-preemptible? Okay, it should be the other way, right? It should be the non-preemptible, right? For deadlock to happen, you have to have non-preemptible resources. You have to do hold and wait. You have to do circular wait, and you have to, what's the other one? I forget. What's the fourth one? You have to have non-preemptible resources. You have to do hold and wait.
Mutual exclusion.
Yeah, mutual exclusion. You only want, yeah. And the circular wait, right? So all of them have to be true, right? So you don't care about deadlocks for preemptible resources, right? So these resources have to be non-preemptible because they're the ones you care about, right? So applications may need preemptible and non-preemptible. We don't care about preemptible because those can never get you to deadlocks. We only care about non-preemptible, right? So in this case, there are 10 instances of A, 5 instances of B, and 7 instances of C, right? So at this particular moment, right, each of the processes 0 through 4 asked for this many resources, right? And so this is how many they are already been allocated, which means that they can potentially ask for this much in the future, right? And you have that many resources available, right? You only have that many resources which were allocated. And if you can look at this, the system can never support, if all of the processes came in and asked for all the resources, it cannot be given to them immediately, right? At the exact same moment, right? Because there's only, like for example, A, there are only 10 instances, and process 0 wants 7, and process 1 wants 3, and process 2 wants 9. You can't possibly give 10 among these three because there already is 19, right? And if you go on, there are more. So there are more resources that people want. So you're trying to find a way in which I can give the resources and still be okay, right? If the amount of resource available was infinity, then you don't really care because you have enough resources, but that's not the case, right? So you have this stuff and you have the available to be 3, 3, and 2, right? So the safety algorithm tries to figure out if you're in this state, in the worst case, if all the processes P0, P1, P2, P3, and P4 come and ask for all the stuff that they need, right? Can they be serviced? Even though they may have to wait, can they still be serviced, right? If you reach a point where they cannot be serviced, then you get into deadlocks, right? And one such situation is P1, P3, that one, and we'll see how that works, right? Let me see. So the way you run the algorithm, you try to assign what you have available to the different processes, right? And see which one can finish, right? So for example, let's look at resource 3, right? Process 0 wants 7, process 1 wants 1, process 2 wants 6, 0, and 4, right? So we only have 3 available, right? Which means that I cannot first schedule process 0 or 3 or 2 or 4, right? Makes sense? I only have 3 of the A available, so I can't possibly give them to 0 or 2 or 4 because they want more. So if they ask for more, I can't give it to them. So that means they're not satisfied with what they have. That means they're not going to release what they have, right? They're not going to finish and release what they have. So the potential set is either P1 or P2, right? At least for A. So I'm trying to find out of the P3, which ones I can give all the resources that they would want from what I have. Since I have 3, 3, and 2, I can either give it to 1 or 3, right? So that means I give the resources to 1, 2, or 3. So if I give it to, let's say, 1, right? That means I hope you can see if I write right below, right? So if I give it to 1, that means the available would become 2, 1, 0, right? Can you see? If I give the available resources 3, 3, and 2 to process 1, which wanted 1, 2, and 2, the available will become 2 because I took 1 of A and 2 of B and 2 of C. So it become 2, 1, and 0, right? So you can let P1 run for however much time it wants. When it finishes, it'll release 3, 2, 2, right? Because that's what it had. So when it finishes, it'll release 3, 2, and 2, which will become 5, 3, and 2, right? So available will become 5, 3, and 2 after P1 finishes, right? Does that make sense? So when I allocate it, it'll become 2, 1, and 0. But when P1 eventually finishes at some point, it'll release all the resources it had. And since it had 3, 2, and 2, it'll become 5, and 3, and 2, right? The next step you're trying to see, if you had this as the availability, 5, 3, and 2, and you only have processes 0, 2, 3, and 4, is there some process which can use this and finish, right? So let's see, right? Which of the processes do you think can benefit from 5, 3, and 2? So P1 is gone. So we have P0, P2, P3, and P4, right? Can you give it to P0? You can't because P0 needs 7 and you only have 5, right? Can you do that to P2? No, right? Can you do that to P3? So you can either give it to P3 or P4, right? Because this one wants 0, 1, 1, or this one wants 4, 3, 1, right? So 4, 3, 1 can be serviced here, 0, 1, 1 can be serviced here. So you have to look at one. So which one do you want to do, P2 or P3? Which one do you want to investigate? P3. So we give this resource to P3, right? Which means that the available would now become 5, 2, 1, right? Because P3 wanted 0, 1, 1. So 0 becomes like A will be 5, this will be 2, and this will be 1, right? So available becomes 5, 2, 1. And P3 makes progress. So we have P1 finished, and let's say P3 finishes, right? When P3 finishes, he'll release all it had, and it had 2, 2, and 2. So when it finishes, it'll be 7, 4, 3. Right? If P3 finishes, you'll have 7, 4, and 3 available, right? So next you're trying to figure out who can be serviced with that one. And turns out actually P0 can take 7, 4, and 3, right? So you keep doing that. So you keep doing this. So let's say we go with P0, right? That means available will become 0. And P0 will proceed. When it finishes, it'll release 7, 5, and 3, right? Which means that available will become 7, 5, and 3, right, after P0 finishes. And then we have to see which one can go, either P2 or P4, right? Let's say we go with P2. That means available will become 1, 5, and 3. And when P2 finishes, it'll release 9, 0, and 2. So that will be 10, 5, and 5, right? And the last one left is P4. And P4 wants 431 can be serviced. And you can release whatever, right? So we are done, right? So we have found a way for all this to finish, which is P1, P3, P0, P2, and P4. If you took this particular route, then all of the processes can finish with the resources they have, right? Which is sort of a little different from what the book gave, but that's okay. The sequence we went was P1, P3, P0, P2, P4. The example that the book gave was this. So there are multiple different sequences how you can solve that, right? You only need to find one. As long as you can find a sequence where all these things can work, this is a safe state, right? Because there's no possible way you can get into unsafe state, right? This does not say that you're going to get into deadlock. All it says is you will never get into the unsafe state, which is what you're trying to see. You're being extremely conservative. We don't ever want to be in an unsafe state. Does not show that whether you're going to be deadlocked. All it says is you will be in an unsafe state, right? So you have to do this every time. So every time you have to allocate something, I have to run this algorithm. So I'm not going to go through this example in class because you can kind of follow along, right? So the thing is, if you ask for so if P1 asks for 1, 0, and 2, right, which is the case here. So process 0 comes in and asks for 1, 0, and 2, so which is well below what it wants to ask. And you have to see, okay, if I allocate this resource to process 1, will the new state be safe, right? So you have to run the algorithm again, find a sequence, and if you follow along, this particular sequence will get you out, right? That means if the process 1 came and asked for this resource, I can still allocate to this one, because if I virtually give this process to give the request to the process, and I ran the safety algorithm, this particular sequence will still get me out, right? And I'm going to let you walk through this stuff. There are 2 other sequences that are out there, right, which you can decide whether it'll work, right? Both of them does not work, right? So if you have 3, 3, and 0, after you do this, you have available as 2, 3, and 0, right? So this request cannot be solved because you're asking for 3 of A, 3 of B, and 0 of C, but you only have 2 of A. That means this particular state cannot be solved because you cannot make progress, right? So if somebody comes and asks for this stuff, they have to be thrown away because allocating that resource is not possible because you don't have enough resources. Even this state is not possible, right? You can run through, because if you make this request and if you give the resources to that particular process, there is no way you can be in a safe state, right? So after you allocate this, if either of these requests come, the bankers algorithm will run through the stuff and say you're going to get into unsafe state. Unsafe state means that you may turn into problem. You don't have to be, but the system has to reject those stuff, right? So it cannot give the resource, right? So that's the banker's algorithm. We're trying to find out if there's any sequence in which it can service, right? Does that make sense? So why do you think operating systems do not? I said operating systems do not implement any of this stuff, right? Why do you think they don't implement this? I think I said the answer in along with discussion, but why do you think they don't do deadlock prevention? What I guess? There are many different reasons why you may not want that, right? Or you can think of other way. Do you think that operating systems should provide the service? Yes?
I was thinking if it detects incorrectly, like the normally running program just could have known a certain operating system.
So when you say incorrectly, right, do you mean that the algorithm is faulty, or?
Well, if the operating system thinks that the program is deadlocked, it's not, like it's just taking really long for something, rather than that program.
So we haven't looked at detection yet, right? So what we looked at so far is avoidance, right? So that means that before I give you something, I have to detect, right? So this is like, I mean, don't look at this slide. This is for the next case where I let it go and then you get it into a deadlock, right? So far, the banker's algorithm says that I'm going to make a decision on whether I should give you a resource or not based on whether you could potentially get into a deadlock, right? So in that case, there is no possible way for you to be in deadlock. If the algorithm was running correctly, I would have never allocated resource to you where you could possibly be in the unsafe state, right? So deadlock can only happen when you go from safe to unsafe to deadlock case, right? So you shouldn't be in a case where you were deadlocked, right? Because you can't possibly be in a deadlock, right? It's very conservative, and that's one of the answers, right? It delays your request if it thinks that there's a possibility that you can get into a deadlock, right? Which may be a good thing, but that means your programs will run slower because it says that there is a possibility that you can get into a deadlock, so I won't let you get that, right? So it's good because it will never get into deadlock, but it's bad because your programs will all slow down, right? All your programs will slow down because it will say, I cannot give you resource because in the worst case, if everybody else who's asking resource, if they come and ask for resource, then I may get into deadlock, so I cannot give you, right? And most of the time, you don't want it to be that correct. We are willing to say, yes, I know in the worst case, I may get into deadlock, but in the normal case, I may not get into deadlock, so let me go, right? That's one of the reasons why you don't want to do this stuff. And the other reason is you have to run this algorithm all the time, right? And it's not a trivial algorithm to run, right? In fact, I think there's like O of n squared different possibilities. You have to look at all the possibilities to see if you get a way out. And that could potentially be slow. So you're making the operating system run complicated algorithms, and you're also trying to be more conservative than you have to be. For the most part, we say, no, we don't want that. We'll just live on the edge. Let's move forward, right? So if you live on the edge, you may get into a deadlock, and the problem that you mentioned comes through, right? Which is, I'll let the processes go, and now they are not making progress. So how do you know whether you're not making progress because you got into a deadlock or because you're just busy doing a lot of computation, right? And that's part of the notion of how do you do deadlock detection, right? So in this case, we let the system move forward. In the previous case, you could never get into deadlock because you're making sure you don't go into unsafe state at all. Here we let it go into the unsafe state and see what happens from there, right? In real operating systems, you don't even do that. You don't even think about any of this stuff. But maybe not for too long because we'll have to confront this sooner or later, right? So the idea here is you can. So now that when you ask for a resource, I don't particularly care whether I can give it to you or not, right? Whether it'll cost me to go into unsafe state. If you ask for a resource, I give you the resource. So now we have to keep track of some state where we periodically look to the system to see if you might be in deadlock, right? By basically trying to see, you ask for a certain resource, and every so often I check to see, based on the resources that were allocated, whether you're actually in deadlock state or not, right? And if you're in a deadlock state, we have to do something. If you're not in a deadlock state, at least I know based on how many resources you wanted and what you had, right? And one of the ways to do that is to maintain a weight graph, right? Which is sort of like a resource allocation graph, and you just twist it like this. So essentially, when you had the resource allocation graph, where you had the process and resource, and so in this case, P2 is requesting R4, and R4 is allocated to P3, right? You change that to P2 waiting on P3, right? You just remove the resource and make a arrow from, if there's an arrow from P2 to R4 to P3, just make it like this, right? P2 to P3, right? So you create that graph and see if there are loops, right? If there's a loop, in this one, then there's a circular wait, right? And this works if you have only one instance of each resource, right? If there are multiple instances, then it becomes complicated. So for now, if you assume that there's only one instance of each resource, then you can take your resource allocation graph, transform it into the corresponding weight graph, and see if there's any circular weight. If there is, then the corresponding processes are deadlocked, right? So periodically you run this algorithm. Periodically, if you have a resource allocation graph, you create the weight graph, run this algorithm to see if there's circular weight. If there's a circular weight, you're in deadlock, and let's see what we can do about it in the next few slides, right? But the problem is you're looking at a live active system, so the system may be transforming halfway through, right? So if you're looking at a big system, right, and I'm generating this graph, right, halfway, so I may have started this at 10 o'clock, and this, by the time I got this, it may be 10:01, and this may be 10:02. I'm exaggerating, but you get the idea, right? So half the graph may have been old, and half the graph may have been new. So it may look like you are actually in a circular weight, whereas it may not actually be, right? It might be that after you constructed this part of the graph, these processes release some resources where they change, right? This is an active system where things are changing all the time. So you get into a race condition where even though you see a circular weight here, it may or may not actually be a deadlock, but it's potentially a deadlock, right? How can you solve this problem? How can you solve this problem of things changing under your feet? Is there a way you can solve this?
You can interrupt everything. You can stop every other process.
Yeah, you can stop everything, right? If periodically when you're doing this, you can stop the whole system, give no allocation to anybody, and then run this algorithm to see if there's deadlock, right? And that would solve this particular problem, but it will be bad for everything else, right? Your system will frequently freeze while it's trying to see if it's a deadlock, and then it'll unfreeze, right? You don't really want that, because you don't really want if your machine was every minute or so suddenly froze for a moment while it's doing this calculation, and then it comes back and says you're not in deadlock, right? And these algorithms are graph algorithms which are very complicated. It's order of n squared, and you'll learn in algorithms what that order means. Order of n squared means that if you have n number of resources, the time it takes to compute this depends on the square of the number of items, right? And that's a big number. So if you have 2, it takes about 4 times, and if you have 3, it takes about 9 times, and if you have 4, it takes about 16 times, and so on. So it's exponentially increasing, right? So the more resources you have, the more time it's going to calculate. So if I have to freeze the whole system while I'm doing all this stuff, you may not like that for the most part, right? So that's the challenge. So you draw this graph. If you have lots of resources, then it's probable that half the system is kind of changing as we go along. You don't want to stop the system, and how do you do this stuff, right? The other way to worry about is if you have resources which have multiple instances, sort of what we looked at before, right? Then the weight graph would be more complicated, because you have multiple resources that you could be allocated to different processors. So you'll have to run sort of the Banker's algorithm kind of stuff. So you see the same kind of nodes, maximum resources, and available, and try to see if the given state is safe, right? So periodically you kind of look at the state of how much was allocated to different processes, and see if there's a possible way that they can get out, right? It's very similar to the Banker's algorithm. And if it finds that you're in an unsafe state, you think that you're in deadlock. And that's the thing. So if you have resources with only one instance per resource, you can do the wait for graph. Multiple instances per resource, you'll have to do the full algorithm. And all these algorithms are complicated because these are graph algorithms. And graph algorithms tend to be complex, right? And so you don't want to run it too often. But if you run it very rarely, then you could be in a deadlock state for a long time, and you don't realize it. So you have to find the balance of which way to go, right? And that's the challenge for any operating system which wants to build this. And I'm not going to go through the example, but it's essentially like what we did for the Banker's algorithm, right? You're trying to see with the resources whether it's in a safe state or not, right? Right. So just like we went through before, right? The real challenge when you do the detection is how often do you run it, when you run it, and what to do about it, right? I mean, all the things we talked about was you come up with the deadlock stuff, and you detect there's a deadlock. What you do with it is one problem, and how often do you run this too, right? If you want to run it every second, then you know immediately when you get into a deadlock, right? You may either want to do it prevent deadlock, which is before it ever happens, but that is too conservative because then you don't even want to go into unsafe state. If I let you go into unsafe state, I would like to know as soon as possible whether you're deadlocked. That means I need to keep running this every so often, and that's also problematic, right? So if I run it very sparingly, then that means you could be in a deadlock and I won't know about it, right? Why would I care whether somebody is in deadlock, right? Can deadlocks spread? Is there a reason why I should worry about deadlock, right? So suppose there are two processes which are deadlocked, right? Suppose there are two processes, you guys are deadlocked, that you are wanting some resource. And there are, let's assume all of you are processes, right? There's only two processes which are deadlocked. Do I, as operating system, need to worry about that there's a certain process which are deadlocked? Do I need to detect it soon? Or can I just wait and detect it once a day? Why would I care if deadlocks are happening in the system? Or should I run the detection algorithm every so often? Yes?
If anyone else needs the resources, they'll be deadlocked too, and you could quickly do it.
It's slowly like sort of like a disease, right? So if they're both deadlocked on something, if they're not sharing any other resource with anybody else, they're fine. But they already have resources. One of the conditions for deadlock is they have to do a hold and wait. So they have some resources that they're holding and they're waiting for something else. So if any of you want one of the resources, then you get a deadlock. Because they get deadlocked, that means you'll get deadlocked, right? If you want one of the resources that they have, it's not preemptible, so I can't take it from them. So any resource they have is potentially spreadable, right? So if any of you want that resource, it'll start spreading. So slowly it'll spread to the whole system, right? So unless I do something about it, the deadlock won't spread, right? Some of you may have noticed this on your PC, right? Sometimes you may have noticed it if you I've noticed it when you pull the plug on, say, a hard disk or something, right? Suppose you pull the plug on hard disk, external hard drive or something. Sometimes because of some bug in the operating system, some process may want to write to that file system, right? So it'll deadlock, right? And you'll slowly see, I don't know how many of you have seen this, but you'll see that your system is working fine. But if you start to write a file, if you start writing your program, so you can work in your PowerPoint for all you want, but you can't write to the thing. So the moment you want to write, then it detects that it needs the resource, it's no longer available, it'll deadlock, right? So you'll be in this state where everything is fine. You can't shut down the system because if you want to shut down, all the applications want write to the last, before they go. So they're in this state where the moment you start writing files, that particular application will keep going up. How many of you noticed that kind of a case? A few of you have noticed it, right? So you're in the state where things are going bad. You can kind of see, you know that things are going so you can't even shut down the system, right? Because every shutdown system will try to write something. So your system apparently looks fine, but practically you can't do anything. So it kind of crashes in like that case, right? So that's what you want to avoid. So you don't want to leave the deadlocks on for too long. You want to be able to get rid of them because it'll kind of keep spreading. As long as anybody else wants the resource, it'll slowly start spreading. So that's the reason why you want to run it more often, right? So deadlocks are really bad. So if you ever get into deadlock, what do you do usually for people who notice deadlocks? What do you do?
Power down.
Yeah, you reboot, right? Because if you get into a deadlock state, the solutions you can think of are, let's say, you can abort the process, right? Frequently, you can't abort the process, but if you want to abort the process, you have to figure out which processes to kill, right? You can kill all the processes, or just start doing from one and hope they'll get out, right? You can have different heuristics. You can look for the program which has been running for the least amount of time, start killing that, and what have you. But there's really no science behind it, right? You have to start off doing the stuff. The reliable way is to reboot the whole system, and then it kind of you kind of get rid of the deadlock, right? But once you get into deadlock, your system is kind of on its way down. You may do some of this stuff about killing some processes. So it depends on what resource it is. If it's a semaphore or something, killing a couple of threads would help you. If it's a printer or something or a hard disk, then you are kind of out of luck. You have to reboot the whole system, right? And that's the challenge with the aborting, right? You have to figure out which order to abort and all those things. For most of you, it makes really no big difference. If you're having a laptop or something, if you have to reboot, you kind of are upset. You're kind of okay, right? I mean, you have to get over it, right? Because that's how we trained you to say, rebooting a laptop, you shouldn't really complain. Just get on with it, right? But that's not the case in all the scenarios, right? So when I was an intern at IBM, one of the things that they were talking about was they have some installation of their mainframe operating system running in Bank of Japan, I think, right? But the operating system has been running on the machine for the last, I forget, 10 or 15 years, right? It's been running without reboot on that machine for the last 15 years, right? Because it's controlling the Bank of Japan, right? So it's controlling, it's the nerve center. So it's running for the last 15 years, right? Which does not mean that the hardware that it ran 15 years back is the same hardware that is running right now, right? The operating system is designed in such a fashion that you can unload the module for a separate thing. So you can unload the module for the disk drive, remove the disk drive, put a new disk drive processor, and then load a new module, and it'll keep running, right? It's kind of a weird model where the operating system is continuously running, even though all the hardware was replaced in the 15 years. You don't want to use the same hardware, right? So every so often you replace the hardware. And they also replace the CPU like that, right? So they can, when you're running the processor, if you have multiple processors, at one instance you can tell the operating system, do not use that processor anymore. I'm going to replace it, put a new one, and then tell the scheduler that now you have a new processor, you keep running, right? So it ran for 15 years, even though it's not actually running on the same hardware, right? And you want to upgrade the operating system with that kind of a system, right? And this is a point of pride for IBM, right? I mean, this is machines have been running for a long time, right? So on those machines, you have to do all the stuff, right? It's not okay for IBM to say, tough luck, you have to reboot the system, right? Because rebooting a system like that is very complicated and all those things, right? And that is what the kind of world you live in dealing with the stuff, right? Your ATMs and all those things. How many of you would be happy if you go to the ATM machine and it says, rebooting, come back in half an hour, right? Because these are big machines, right? So those kind of systems, you have to worry about all the stuff. I mean, I can tell you, if you're using a PowerPoint, just reboot, right? How many of you were happy when if I were to say, if a machine deadlocks, just reboot the machine, it'll be fine, right? How many of you said, oh, that's no big deal, and reboot the machine, right? And how many of you were in a position where you said, no, not now, right now, because I need to submit something right now. And no reboot now, maybe later, right? How many of you were happy if I said, oh, rebooting is fine? But I don't think anybody would say, oh, that's okay, right? But that's how we've been, as community operating systems have been dealing with. I mean, if you talk to Microsoft or something, they've been saying, just reboot, it'll be fine. Same for Mac or same for Windows, right? But we have to go into this model because as you have more processors, you go more and more into these conditions where you can get into deadlocks. But as you depend more and more on computers, it's not okay to say those things. So we need to address these kind of issues. There are next some slides on how you may do this stuff. But the essential point is current operating systems do not do any of those stuff. They don't do detection. They don't do avoidance. They just give whatever resources you want. If you get into a deadlock, it's up to you to figure out which process to delete and which process to move along, right? But I don't think you can keep doing that for too long because the probability of deadlocks keep going up as you have more processors, right? Future is more processors. So you are going to get into more deadlocks. So you can't keep ignoring this problem for too long, right? So that kind of concludes these two modules, right? And I'll do a survey, but if you have any thoughts, if you want me to go over some of the stuff on Friday before you go to the next module, let me know, and I'll see you guys on Friday.